Imagine the sun's core, a place of intense heat and pressure, a crucible where hydrogen atoms merge to form helium, releasing a colossal amount of energy in the process. This, in essence, is nuclear fusion. Nuclear fusion is a process that happens under extreme conditions. We're talking about temperatures in the range of millions of degrees, far hotter than the core of the sun. This intense heat is necessary to overcome the natural repulsion between atomic nuclei, allowing them to collide and fuse. But temperature alone isn't enough. We also need high pressure, akin to the immense gravitational force inside a star. This pressure keeps the hot plasma, a state of matter composed of free electrons and atomic nuclei, dense enough for fusion to occur. And let's not forget the actors of this grand play, light atomic nuclei. This process requires the lightest of elements, usually isotopes of hydrogen like deuterium and tritium. When these light atomic nuclei collide under the right conditions, they combine to form a heavier nucleus, typically helium. The mass of this helium nucleus is slightly less than the sum of the masses of the original hydrogen nuclei. This tiny bit of missing mass is converted into a massive amount of energy. Now, recreating extreme conditions here on Earth is the real challenge. It's like trying to create a mini sun right here in our backyard. We need to heat the plasma to incredibly high temperatures, maintain an intense pressure, and do all of this while containing the plasma to prevent it from touching and melting the walls of the container. And we need to do this in a way that's safe, sustainable, and ideally produces more energy than it consumes. Creating a mini sun here on Earth is a daunting task, but humanity has never shied away from a challenge. And with the promise of virtually limitless clean energy, the prize is worth the effort. This is the quest for nuclear fusion. The quest for nuclear fusion, the holy grail of energy production, has been a scientific odyssey spanning decades. The journey has seen the development of impressive machines like tokamaks and stellarators, designed to confine and control the plasma necessary for fusion reactions. These devices, with their twisted magnetic fields, are testament to the ingenuity and tenacity of the scientific community. Moving forward, the world's eyes are on the International Thermonuclear Experimental Reactor, or ITER, a collaboration of 35 nations that aims to make fusion energy a reality. This ambitious project, currently under construction in France, is expected to produce its first plasma in the late 2020s and to achieve full fusion power by the mid-2030s. While we are still some way away from having fusion power plants, significant strides are being made in the right direction. The dream of harnessing the power of stars here on Earth is closer than ever before, and the scientific journey continues. Now, you may wonder, what happens if we crack the fusion puzzle? Let's explore that. The first and most obvious benefit is abundant energy. Imagine an inexhaustible source of power that could light up our cities, power our industries, and charge our electric vehicles without a hitch. But it doesn't stop there. This could reduce our reliance on fossil fuels, cutting down on harmful emissions, and playing a significant role in combating climate change. Moreover, unlike its cousin, nuclear fission, fusion produces minimal radioactive waste, making it a much cleaner energy source. And the possibilities seem almost limitless. Fusion could revolutionize industries, from manufacturing to transportation, by providing a virtually endless supply of clean power. It could even accelerate space exploration, as fusion reactors could potentially power spacecraft for long-duration missions. Short, nuclear fusion has the potential to propel humanity into a new era of technological advancement and environmental sustainability. With great power comes great responsibility, and nuclear fusion is no exception. As we explore the realm of nuclear fusion, it's natural to question its potential for weaponization. After all, we've seen the destructive power of nuclear fission in weapons, and it's a chilling thought to imagine that power amplified. Yet, while fusion reactions release more energy than fission, creating a fusion weapon is not just a matter of scaling up. It presents formidable technical challenges. Fusion requires extreme temperatures and pressures far beyond what's needed for fission. Moreover, achieving these conditions in a controlled, portable way, as would be required for a weapon, is currently beyond our technological reach. Furthermore, the international community has regulations in place to prevent the weaponization of nuclear technology. The focus of nuclear fusion research is firmly on energy production, not weaponry. The potential for weaponization exists. The focus remains firmly on harnessing fusion for peaceful purposes, lighting up our future in a way we can hardly imagine.